Hi everybody, this is Ahmed Mahfouz. Today I'll be presenting my CS657 final project. This project is about time series forecasting. What motivated me is that time series forecasting has been playing an essential role in various industries, like stock market analysis, sales forecasting, economic forecasting, and many other industries. In this project, I'm exploring the implementation of different forecasting models while employing Spark capabilities, mining large data sets. After doing some research, I found two popular models that are heavily used, Arima and Profit. So after deciding which area I would like to explore, I started looking for a suitable dataset that could help me achieve this goal. And after some research, I found a Kaggle competition sponsored by Google that was closed like 4 years back. It is a forecasting for the web traffic to Wikipedia pages. The training dataset consists of approximately 145,000 articles traffic data with a total size of 265 MB. Each row represents the daily views of a Wikipedia article, starting from July 1st, 2015, up until December 31st, 2016. Since this is a competition, I don't have this data, but I will be using the data from July 1st, 2015 till October 30th, 2016 for training, and for testing and forecasting the traffic, I'll be using from November 1st, 2016 to December 31st, 2016. The data is available in CSV format. Each record contains 550 columns, each representing a day in the date range of the dataset. Each day column has a value corresponding to the number of hits for the Wikipedia article on that day. As you can see here in the table, and since the data is in a compact format, which is not time series setup, we need to do some pre-processing to get the data in a form that we can easily feed to our models, which is a date and number of hits, as you can see here in the table. Transposing the data produced 63 million records, but using Spark muscles, I brought the size back down to only 550 rows, and that's after grouping the data back again by date. The data is now ready for our first model, Arima. Arima stands for Autoregressive Integrated Moving Average, a combination of the autoregressive and moving average model. In a nutshell, the AR model makes its prediction based on the past values, but on the other hand, the moving average model makes its prediction on the mean and past errors. When using these models, there is a constraint that we need the data to be stationary, which means it has a constant mean and constant standard deviation. After plotting the data to inspect it visually, as you can see in the graph, it doesn't look stationary, but still, we can do a test called augmented Dickey-Fuller test to verify, and as you can see here, the results from the test show that the p-value is high, which means we have no substantial evidence that the data is stationary. That's a bummer, but we can still use the data by applying the difference transformation. And we can create a stationary data using this transformation, and that's by subtracting the value at time t and the previous one at time t1 minus 1. And the Arima model will help us automatically do this transformation. The Arima model needs three parameters, P, Q, and D. P, which is the number of past lags or past times for the autoregressive model. Q, which is the number of transformations that we need to do to make the data stationary. D, which is the number of lags or previous times that we will use for the moving average model. To identify the best value for P and Q, we can use two graphs, ACF, autocorrelation factor, and the PACF, which is the partial autocorrelation factor graph. The ACF graph will help us set the D value, and the PACF can help us select the B value. In the ACF graph, anything outside the blue boundary is considered a significant correlation. So the ACF, the loss significant correlation is 27, and the PACF, the loss significant correlation is at 21. Now we have our P, Q, and D values, we can start fitting our training data and predict our test data and make a forecast. Alright, here are the results. Looking at our forecast, it seems to be very close. It might have missed the spike, but mainly it has produced a very reasonable prediction. The SAMPE produced is as well very low, 5.7. Now let's take a look at the profit model. The profit model is different than the Arima model. It is based on a decomposable additive model where nonlinear trends are fit with seasonality. It also considers the effect of holidays. The profit model has so many parameters, but we will focus only on the seasonal ones. But first, let's see if we have any seasonality pattern in our data. Visually, in inspecting the data, we can see the trend up, but we cannot tell if there's any pattern. After zooming in, we can see a weekly seasonality pattern, which is our lead. So we will set the weekly seasonality pattern parameter to true. Now let's fit our training data and make a forecast for our test data. Here you go. The profit model has produced very good results, very close to the actual data. Still, it has missed the spike like Arima. Still, the prediction has a good SAMPE of 6.9. After completing the forecasting for the whole traffic, I also wanted to forecast each Wikipedia article traffic using the Arima model since it performed better. I took first a random sample of the data and applied the same model I used for the overall forecasting. It produced a good result with SAMPE of 45, which is relatively good compared to the competition leaderboard, which the winner scored 34. But applying the same model with all of these coefficients, all of these variables for 145,000 articles will take forever. So I decided to go with just one significant past variable. The pages forecasting produced SAMPE of 58, which is not great, but that was the cost of reducing the number of variables to make the forecasting faster. Alright, here's the conclusion. The Arima and Profit models have produced very similar results. However, the Arima model has been slightly better. The Profit model was much easier to set up, and it didn't need much data examination to produce good results. The time series data volume nature is enormous, but Spark can help aggregate and reduce the data very effectively by distributing the data and the operation across all the cluster nodes. The Profit and Arima models aren't part of the MLab library of Spark. They use Pandas data frame as an input, which is not efficient when dealing with large datasets, but aggregating the time series and chunking them can help apply different models across different chunks. Thank you.